Alright, now let's put it all together and do this fantastic problem about figuring out where Thelma and Louise would land if they drove off a cliff. So our question is basically figure out how far horizontally they travel. And they're driving some kind of weird rectangular nosed dolphin, it seems. Alright, so we can see this in our mind. The car is going perfectly horizontally with no vertical component in its motion the instant it comes off the cliff. So that's pretty simple. All the velocity is in the x direction. But in our mind we can see it kind of falling. And as it falls, we know that gravity is going to accelerate downward, and it's going to have a y component of its velocity also. So we can, we know that the overall final velocity, like the instant before it hits the ground, right before it hits the ground, is going to look probably like this. But what we need to realize is that we can separate this into the x and y components of that final velocity. And when we realize we can do this, we realize that it's a much simpler situation than we thought, or that it looked like, because we can figure out what Vx is, because was there any horizontal acceleration while the car was in the air? No. They can spin their tires all they want. There's no ground to provide a force on the tires to accelerate them. Gravity acts perfectly vertically, so there's no component of gravity that is going to accelerate them horizontally. Okay, so the air resistance might slow them down a little bit, but let's pretend that doesn't happen. Because we often ignore air when we're doing these first semester physics problems. So that leaves us, we've concluded there's no acceleration, then the velocity must not have changed, and Vx must be still 40 meters per second. And this Vx, this horizontal component of the velocity, is the most important component because this is the component that is making the car go forward and travel over more horizontal distance. So we're seeing that this could be a simple problem that we could solve with skills from chapter 2, because we know that change in displacement, here's our horizontal distance traveled here, is the average velocity times the elapsed time. And it's easy to find the average velocity because it's constant. If it's a constant 40 meters per second, then the average is clearly 40 meters per second. If only we knew the time, we can figure out the time. To figure out the time, we just need to look at the vertical component of the motion, ignoring how far it's traveling left and right, but just think about the drop. And here are the things we have to think about. We know it is dropping a total distance of 100 meters, and we know that it's accelerating downward with the acceleration of gravity during that entire period. So So here's what variables these numbers represent. And we usually write, delta x as a displacement, but here we could use any other variable we want. We could use a, b, z, but here let's use y because generally y means vertical. And this will be our acceleration, and we'll give a little y subscript to show that this is a vertical acceleration. And we also know that at the instant the car goes off the edge of the cliff, at the very instant it goes off the edge, it's not moving downward or upward. Even though it's moving 40 meters per second sideways, its vertical Vy velocity is 0 because it's not yet falling. So that's a Vy initial. Oh man, we have to get two subscripts going on there. So knowing all of these things, we can find a chapter 2 kinematic equation that has delta t in it and solve for delta t, such as this one. And let's just translate that. Instead of delta x, we've decided our displacement we're going to call delta y. And our initial velocity is vyi instead of, well, we could write it vo or vyi here. And here our acceleration a is really the acceleration of gravity, so we can go ahead and write g in there. And that's our equation that we use to solve for t. And we know that since the initial vertical velocity is 0, this term just is 0. So our equation simplifies to this, and now we just solve for t. I divided both sides by 1/2 g to give us a solution for t squared, and now we just have to take the square root of both sides to get t. And here's where we could put in values for delta y. We could put in 100 meters for delta y, and then we could put in 9.8 meters per second squared for g and get a number for time. Or we could just take this definition for t, and this is actually delta t. We could take this definition for delta t and insert it in place of delta t in our equation that we're using up here. Remember the simple one that'll give us our answer if only we knew delta t? So I'm going to rewrite the equation, and instead of writing delta t, I'm going to write what we found for delta t. 2 delta y over g. And now I have put in the numbers for delta y and g, and my calculator tells me that that is 180 meters. So that's 180 meters of horizontal distance. Okay, let's rewind a little bit and do that in a very similar but slightly different way. Let's actually find the time of flight. We saw that we can just look at the vertical motion and use this equation to solve for t. And that's what we got when we solved for t. And then we put in our numbers, and this is 2 times 100 meters of vertical distance divided by the vertical acceleration of 9.8 meters per second squared. And this is basically the square root of a little bit more than 20, which comes out to 4.52 approximately, and that is seconds. And again, we found time just by looking at the vertical motion. And the second step is to take that time and look only at the horizontal motion. And we know that our horizontal velocity remains unchanged at 40 meters per second the entire time. So if we have a constant velocity and a known time, it's pretty easy to figure out the distance traveled, which is that velocity multiplied by the time of flight. We just found that time of flight, and we should get the same answer we just had before. Yeah, about 180 meters.
Made with Doodlecast Pro.